So good morning, everyone. Welcome back to the Algebraic Graph Theory seminar. Today, it is my pleasure to introduce Sidhanth Mohanty from the MIT, and he's going to talk about explicit lossless vertex expanders.
Yeah, thanks so much for coming, and thank you for inviting me to speak at the seminar. I'm honored to be here. And today I will talk about explicit lossless vertex expanders. And the talk is going to be based on two papers. The first one is joint work with Tim Hsieh, David Lin, Ryan O'Donnell, and Rachel Zhang. And the second work is also joint work with Tim and Rachel, and also Alex Lubotsky and Asaf Reiner. Okay, so let's jump into the math of the talk. So first I'll define this notion of lossless vertex expansion, which is going to be the key subject of this talk. So you have an n vertex deregular graph G, such as the one pictured on the left, and let S, the subset of vertices which are colored green, be a small set of vertices. We'll be interested in the vertex expansion of S. So in particular, we're going to say the expansion of S is the number of neighbors divided by the size of the set. And we're going to call this graph G a lossless expander if the expansion of every small set is close to D. So the expansion of any set cannot exceed D. And we care about the notion where where every small set has expansion roughly close to D. And here, when I say small, you should think of the number of vertices in S as being linear in the total number of vertices. That is, the size of S is a small constant eta times the size of the set. And the goal in this talk is going to be to construct lossless expanders of constant degree. And in particular, we will be interested in giving a construction of an infinite family of lossless expanders. So I'll get into the more precise details of what I mean by construction and such. But before I do that, I want to spend a moment motivating why one should care about this notion of expansion. So actually, constructions of vertex expanders have had a lot of uh, different applications to various parts of theoretical computer science and algorithms, and also complexity theory. And I guess I maybe want to spend 2 minutes actually discussing one of these applications, which is due to a nice work of Simpson and Spielman from 1996. So this application is to the construction of these objects known as error correcting codes. So let me define how one uses a vertex expander to construct an error correcting code. So imagine a bipartite graph. And for now, let's say the small sets on the left expand losslessly to the right. Okay, so you should think of each code word as being an assignment of bits to the vertices on the left. So you just label each vertex on the left with 0 or 1. And the vertices on the right function as parity checks. That is, each vertex on the right looks at the bits on its neighbors on the left, computes their sum over F2, and checks whether the sum is indeed equal to 0. Okay, so now this defines some kind of linear subspace of F2 to the dimension of the left-hand side. And in particular, because you put R constraints on the right, the dimension of the subspace is at least L minus R. So if L was even, let's say, 1.1 times R, this is a space of linear dimension. And the claim is, if the graph is a lossless expander, then any pair of words inside the set C are actually of distance linear in the number of vertices apart. And indeed, as you can see on the right, if you have a small number of errors, that is, if you take any member of the subspace and on the right and you add a few errors, then these are going to reflect in some violated parity checks on the right. And in particular, these are going to show up in the so-called unique neighbors of the set, namely which are vertices that have only one neighbor back in the set of errors. And actually, lossless expansion implies that you have a lot of unique neighbors. All right, so if you have a small weight word, then it violates many parity checks. And one nice feature of lossless expanders or codes based on lossless expanders is that you can correct these errors in linear time. Okay, so that was a digression, but hopefully I've convinced you that a vertex expansion is an important notion. And today our goal is going to be to construct constant degree lossless expanders. Okay, so one fact which you can prove via uh, a simple application of concentration as well as a union bound is that if you take a random regular graph, then it is going to be a lossless expander with high probability. Okay, so does this solve our problem? So yes, if our goal was just to show that lossless expanders exist and give some way to construct one um, with high probability, then yes. But today we will be after a more ambitious goal. And the more ambitious goal is to construct these expanders with an algorithm that is deterministic and runs in polynomial time in the number of vertices of the construction. Okay, so now you may ask, why may one care about this particular notion of explicit? And okay, here's one example. So random graphs tend to lack structure that you need for applications. So, for example, in a work of Lin and Hsieh, there's actually a different Hsieh than my co-author on this paper. So they construct um, quantum codes from lossless expanders, but you additionally need the lossless expanders to have some symmetry properties. That is, you want the number of automorphisms that this graph has to be really huge. Whereas a random graph is not going to have any non-trivial automorphisms. So one may hope that in trying to chase after these stronger notions like explicit, as a side effect, you might be able to uh, actually get these extra structural properties. Okay, and maybe a second, more philosophical reason for why I find this problem interesting is even though we know that a random graph is a lossless expander with high probability, it is likely the case that certifying lossless expansion in a random graph is computationally hard. So I could give you a random graph, or I could give you a graph where I adversarially planted a non-expanding set, and you likely won't be able to tell them apart. So it's quite interesting that it's plausible that you might be able to construct an object uh, which supposedly exists everywhere, but uh, checking whether it has this property of lossless expansion is hard. Also, by the way, it occurred to me that I actually cannot see the Zoom chat while I'm screen sharing. So in case there's questions, I would love if like you just unmute yourself and interrupt me. Okay, all right. Okay, so what's the story we know so far? We know that random graphs are nearly optimal lossless expanders. And now, if you've worked in spectral graph theory or expanders for a bit, one natural question you might have, there's this way more common notion of spectral expansion based on eigenvalues. And people have spent many decades constructing many, many different kinds of spectral expanders. So one may ask, how good are these spectral expanders for vertex expansion? And at least that was also my first natural question when I started working on this problem. Okay, so just to recap what the notion of spectral expansion is. So if I give you an n vertex graph, it's going to have, and if I write down the eigenvalues of its random walk matrix, there's going to be n of them. There's going to be the trivial eigenvalue, which has magnitude 1. And then there's going to be the non-trivial ones. And we say a graph is a spectral expander if there's a significant gap between the top eigenvalue and the second eigenvalue. And the reason spectral expansion is an interesting notion is because it implies a lot of combinatorial properties of interest. For example, it implies that random walks in your graph mix fast. It tells you that your graph has no sparse cuts. It also tells you that if you look at a small subgraph, there's going to be not too many edges in that subgraph. And over the years, there have been a ton of constructions that use many different kinds of ideas. For example, there's ideas based on algebra, which study Cayley graphs. There's also this combinatorial idea of this exact product. There's the method of interlacing polynomials. Then there's de-randomizing random graphs, and the list goes on. Okay, so how good of vertex expanders are these spectral expanders? So Cayley in 1995 proved that if your second eigenvalue is optimally good, and here optimally good means the second eigenvalue is at most some number, 2 square root d minus 1. Not so important for today what that number is, but um, graphs achieving this number are called Ramanujan graphs. So Cayley proved that a Ramanujan graph actually has half times d vertex expansion. And it wasn't just that Cayley's statement was loose. In the same paper, um, he gave an example of a near Ramanujan graph where there is a small set of vertices which has expansion actually only at most d over 2. So his theorem of optimal lambda 2 implies d over 2 vertex expansion is actually tight. And later with Theo Mackenzie, we gave pseudo-random graphs which are near Ramanujan, and also there is a set with expansion d over 2. And actually, in a more recent, very striking work of Cumber and Kaufman, they proved that these algebraic Ramanujan graphs also do have small sets with expansion d over 2, and specifically the exactly Ramanujan graph construction of Morgenstern. And this to me was amazing because prior to their work, I thought these small sets with bad expansion were simply things that we contrived, and they probably wouldn't occur in, like, say, natural algebraic graphs and such. But turns out they do. Okay, so what we've established here is if our goal is to get lossless expansion, and in particular stronger than d over 2 vertex expansion, then there's really no link between the eigenvalues of the graph and its vertex expansion. So we would need to go beyond. And actually, over the decades, this problem has been tackled. And people have made progress along various different axes. Most notably, I want to point out these works of Capalbo, Rangel, Vidhan, Vickerson, um, followed by simplifications of Golovich and Cohen-Roth Tashma, which constructed graphs that are one-sided lossless expanders. That is, they construct these bipartite graphs where sets on the left have lossless expansion to sets on the right. But if you ask for a subset of vertices on the right, there's no kinds of guarantees. But this is great because actually a lot of the applications that I mentioned early on in the talk, including the one which I illustrated with error correcting codes, do actually only rely on one-sided lossless expansion. There is a single application to quantum codes of two-sided lossless expanders, which are not covered by any of these weaker variants. Yeah, along um, the lines of other weaker variants people have considered, people have also tried constructing graphs have where small sets have a lot of unique neighbors, even though they fall short of um, having close to lossless vertex expansion. People have also studied the highly imbalanced setting where the left is a polynomial factor bigger than the right. And they've also studied things like instead of linear size sets, what can you say about small polynomial or subpolynomial size sets? Okay, so uh, after spending a bunch of time on this problem with collaborators, we were able to say the following. So in the first paper, we were able to give a construction of graphs where every small set has expansion at least 3/5 times d. And um, building on that work and using a few new ideas, we were actually able to push this needle all the way to obtaining lossless expanders. And this is the main result that I want to highlight in this talk. And actually, the graphs that we construct do indeed have the special symmetries that are needed for certain downstream applications. And we were able to use these to realize quantum LDPC codes with a linear time decoder that where the reduction was done by Lin and Hsieh from quantum codes to lossless expanders. Okay, so I think now's a good time for me to pause for a couple seconds to see if people have questions. All right. So now in the rest of the talk, I want to focus on the ideas that go into constructing lossless expanders. So a starting point is actually going to be this fact that I told you all about early on in the talk, that a random graph is a lossless expander. But in particular, let me tell you all a more quantitative version of the statement. If you have a random graph with capital D many vertices, and it's little d regular, then sets of size up to capital D over little d have lossless expansion. And in fact, you can't hope to do much better than that because any set's neighborhood will at most cover the graph, which has capital D vertices. So you're bottlenecked at capital D over little d. And in this context, you should think of capital D as also being a constant. So it is actually possible for you to perform a brute force search to find this lossless expander. So the first step is going to be to find a constant sized lossless expander. And the idea is we want to somehow take this constant size loss expander that we found and amplify it into a big graph. And now I'm going to spend the next few slides slowly going over this amplification procedure. Okay, so this amplification procedure is actually um, based on a certain product of a big graph that we'll call an amplifier and a small graph that we'll call the proto-lossless expander. And this amplification procedure was something we developed in a joint work with Tim Hsieh, Theo McKenzie, and Pedro Paredes. Okay, so now I'm going to describe how to take a product of this amplifier graph on the left and the small lossless expander on the right. And just to calibrate you all, I want to tell you some parameters of these graphs. So the small lossless expander, like I mentioned earlier, has capital D many vertices on either side, and it has degree little d. Now, the amplifier graph on the left is a tripartite graph. There's a left, there's a middle, and there's a right. The degree from the middle to the left is capital D, the same capital D as the number of vertices on the constant size lossless expander. And you should think of this number k, which is the degree from the left to the middle, as being way smaller than d. Okay, so now let's describe how the product works. So the product is going to be, it's going to give you a graph where the vertices are the left vertices of the amplifier and the right vertices of the amplifier. The middle is going to be removed. Uh, but we're going to do the following. For each vertex V in the middle, we're going to look at the left neighbors of V, the right neighbors of V, and place a copy of this proto-lossless expander between the left neighbors and the right neighbors. Let's see how this goes with a picture. Okay, so here's my amplifier graph. Let me zoom in on one vertex, this red vertex. It has 5 neighbors on the left, 5 neighbors on the right. And I'm going to place a copy of the proto-lossless expander between its 5 left neighbors and its 5 right neighbors. All right, so that's the first copy. Now let's look at the second vertex in the middle, which is a blue vertex. Again, has 5 neighbors on the left, 5 neighbors on the right. Between those, let's place another copy of this proto-lossless expander. Okay, and then I do this the third, fourth, fifth, sixth vertex, and so on. And once I perform this procedure, I have this graph over here, which, okay, at least visually it looks fairly uh, pseudo-random, and it's going to be our task to prove that this graph over here is actually a lossless vertex expander. Okay, but I got to tell you how to choose the amplifier. And actually, the choice of the amplifier is going to be the subject for the rest of the talk. Okay, so once again, to calibrate you all with some parameters, given the parameters of the amplifier and the proto-lossless expander, you're going to get a little d times k regular bipartite graph. And actually, if you wanted to get biregular graphs where maybe the left side has some degree and the right side has a different degree, then you can actually generalize this construction by simply changing the relevant parameters in the amplifier and the proto-lossless expander. Right, and the explicit construction, which was stated as the main result of this talk, can be obtained by suitably instantiating the amplifier. Okay, so now let's jump into the aspect of how one picks the amplifier. So actually, in the original paper that introduce this tripartite line product, one simply uses standard special expanders or bipartite Ramanujan graphs for the amplifier. And this actually does work to some extent in the sense it gives you a unique neighbor expander, but the actual vertex expansion of the resulting graph can be pretty bad. Like there's a concrete barrier. And okay, maybe I should say what exactly I mean by you choose the amplifier as using bipartite Ramanujan graphs. It just means you take two bipartite Ramanujan graphs with where one of the sides has and you put the first bipartite Ramanujan graph between the middle and the left, and the second between the middle and the right. And maybe because we're thinking of the left and right as having the same size, you can even think of taking one bipartite Ramanujan graph and putting two copies of it between the middle and the left and between the middle and the right. Okay, so in the work where we achieved 0.6D vertex expansion, we chose the amplifier based on Ramanujan simplicial complexes. So in today's talk, I will not get into what these things are. I also don't necessarily expect the audience to know what this is. So just think of it as being a black box for now. But the thing I wanted to point out was even though this does break the spectral barrier and it gives you 0.6D vertex expansion, uh, there is actually a barrier to use these as the amplifier if we want to go beyond D over square root 2, which is roughly 0.7D. So at least with the current techniques, we don't know how to say that this graph would give you a lossless expander. And finally, in the most recent paper, we chose the amplifier using Ramanujan cubical complexes. And we were able to show that this indeed does give us a lossless expander. And now, in the rest of the talk, I actually do hope to tell you all what a cubical complex is and maybe a little bit about how using it does help. Maybe this is another junction for me to pause to see if people have questions. Okay, so in the rest of the talk, I'm going to outline some of the desirable properties we would want in an amplifier. And then I'll explain what the cubical complex is, which is the amplifier that we use. And then finally, I'll conclude and tell you all some open problems that I like. All right, so we got this graph from this tripartite line product, and we want to prove that it's a lossless expander. So for any small set S of the left, which has at most small constant eta times size of L many vertices, we want to say that the set of its neighbors is actually a pretty large set. And in particular, we want to say that the ratio of the number of neighbors and the size of the set is approximately the degree. All right, so how would one go about doing this? This is where we would use the fact that the graph that we constructed did indeed come from a product of this amplifier and this particular lossless expander. So in particular, if we take a small set of vertices on the left, all its neighbors on the right are going to be due to some of the gadgets that go, some of the proto-lossless expanders that go through the middle vertices. So in particular, here I highlighted the left vertices in the set in green. The green circle vertices in the middle are the neighbors of the left vertices. And through each green vertex in the middle, you get a bunch of neighbors on the right. Okay, so in order to prove that the graph is a lossless expander, intuitively it suffices to prove two things. The first thing you'd want to show is there's few congested middle vertices. And what does it mean for a middle vertex to be congested? It means that, let's take a middle vertex. Let's call it congested if it has more than some threshold number of neighbors on the left. And the threshold is going to be roughly capital D over little d. Okay, but another source of issues for us, which could hurt lossless expansion, is collisions on the right. That is, if you look at the edges going from the middle to the right, if these edges have too many collisions among themselves, then that really hurts your vertex expansion. So we would like to say that uh, on average, if you normalize by the number of vertices, the number of collisions that each vertex partakes in is a lot less than d. I guess I should phrase that in a more clear way. Let's say I look at a middle green vertex, and let's say we count how many of the red edges that it's shooting out to the right partake in collisions. We would want this number to be a lot less than little d. All right, so I guess I don't want to get too quantitative here so that I'm not confusing. So maybe let's for now only think of the two qualitative statements that we need: a few congested middle vertices and few collisions on the right. And I will tell you all two combinatorial quantities associated to the left middle or equivalently the middle right graph that you should think of, which will control quantities 1 and 2. I won't tell you how controlling the quantities I'm about to tell you will control 1 and 2, but hopefully they're interesting on their own. Okay, so quantity number 1 is controlled by something known as the small set square root k face density. So let me define what this is. So if you take a set of vertices in the middle, such as the ones that I've colored green, and you count how many vertices on the left have more than square root k neighbors in the middle, and you normalize that by the size of S. We call this the small set root k face density. Okay, and now I'm going to define the small set edge density of this set S to be the average degree of a particular ancillary graph we construct called gamma S, where it's a graph on S where we put an edge between two vertices if they distance 2 apart in this particular graph that I've drawn on the left. Okay, so if I can control these two quantities, then it actually implies control over the combinatorial quantities I would need to handle to prove lossless expansion. And again, I won't tell you the exact quantitative bounds that one would need to show on number 1 and number 2. But let me just say two things. The quantitative bounds for number 1 and number 2 that are satisfied by Ramanujan graphs are not enough, in the sense they would actually lead to a set with bad vertex expansion. Okay, but also it if you can give any sort of substantial improvement over Ramanujan graphs, then this would imply lossless expand. This would give you a lossless expander. Okay, so now I want to tell you all about the cubical complex. Okay, maybe before I jump into the cubical complex part, I'll pause here to see if people have questions. All right, so now in the last part of the talk, let me tell you all what a cubical complex is. I want to say if you were lost in the last, say, 2 or 3 slides, it's fine because the description of a cubical complex will not rely on uh, that part of the prerequisite. All right, so let me define a k-dimensional cubical complex. So you should think of having a vertex set, which is 2 to the k partite. And in particular, you should think of this 2 to the k partite vertex set as being 2 to the k copies of the same vertex set gamma. And you should think of these sets as being indexed by k-bit strings of the k-dimensional hypercube. Okay, so these are the vertices of the complex. Now, the complex is also going to comprise of a bunch of cubes. You should think of each cube as being a hyperedge, but it's a hyperedge with a special structure. It's a hyperedge that contains one vertex from each of these 2 to the k parts. So here I've illustrated a cube to you. The hyperedge is simply the collection of the red vertices. Um, I drew the cube just to illustrate that that's how you should think of this hyperedge. Okay, now I want to tell you all a simple construction of a cubical complex. And the construction that we use will be like a more complicated version of the construction that I will show you. Okay, so here's a simple way in which you could construct a cubical complex. You should think of the set gamma as being an abelian group. Maybe if you want to be concrete, you can even think of it as being, let's say, integers 1 to n, 1 through n. Okay, and now let's say I pick k subsets of this group, A1 through AK, and each of these subsets is a generating set. Now, the vertices of the cubical complex are going to be 2 to the k copies of this abelian group. And each cube is going to be described by, first, I tell you a single vertex in part 0, 0, 0. So part 0, 0, 0 is the bottom left part, and part 1, 1, 1 is the top right inside part. So I first tell you the vertex, the member of this cube in part 0, 0, 0. And then I describe k group elements. And in particular, these elements A1 through AK are going to be such that A1 is from the first generating set A1, capital A1, A2 is from the second generating set capital A2, and so on. Okay, now I have to tell you how you draw the cube in this case. So let's draw it progressively. So you start with V. You draw an edge from V in part 0, 0, 0 to V plus A1 in the part where you toggle the first bit. So the part I drew it to is part 1, 0, 0. Okay, and then you draw an edge from V to V plus A2, but because you use second generator, you toggle the second bit. Okay, now you do the same from V plus A1, but in the two direction, and V plus A2, but in the one direction. Notice that because the group is abelian, when you did this, you got a square. That is V plus A1 connected to V plus A1 plus A2, and V plus A2 connected to V plus A2 plus A1, which is the same as V plus A1 plus A2. Okay, now in direction 3, namely, you toggle the third bit, and you go up, you basically go from V to V plus A3, or V plus A2 to V plus A2 plus A3, and so on. And actually, it turns out, due to abelianness, uh, you actually get a complete cube just by drawing the remaining red and blue edges. Okay, so what's the takeaway here? If I tell you a single vertex V, and if I tell you k generators, then that actually automatically gives you a cube just due to the abelian nature. Oops. Okay, so now let me give you what a formal description of the cube is. The cube is going to be V plus. Now, I take sum over xi times ai, where xi is 0, 1 valued. And I range x over the full hypercube. And that's what gives me uh, the vertex in the cube that's in part x. Okay, so one basic observation is that each vertex actually takes part in a1 times a2 times dot 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 ak many cubes. And this is because any choice of generators A1 to AK I could have given you would have resulted in a cube. Okay, so this is like a cubical complex over an abelian group. Actually, just because we want optimal parameters in terms of expansion and such, we rely on a non-abelian Cayley cubical complex, which you can actually construct in a fairly simple way if you take uh, the the so-called LPS Ramanujan graphs as your starting point. And there's a very general version of this which was constructed in a work of Rungtana, Peram, Stix, and Vidovina. So today I won't get into how the non-abelian version of the Cayley cubical complex is constructed. And the main reason to use the non-abelian version over the abelian version is that it gives us pretty strong expansion properties. And in particular, let's say look at any pair of parts that are adjacent to each other. So let's say part 0, 0, 0 and 0, 0, 1. Then actually the graph between these pair of parts is going to be a regular graph. In fact, it's going to be some kind of Cayley graph. And just due to the choice of the particular non-abelian group, this bipartite Cayley graph ends up being a Ramanujan graph. It ends up having optimal second eigenvalue bounds. And this is actually a property that we would need. Uh, and using an abelian group would result in logarithmic losses and parameters. All right, so I guess I told you what the cubical complex is, but I need to tell you how you get an amplifier graph from this cubical complex. Because the amplifier graph was a tripartite graph. So the types don't quite match up yet. So let me do that next. Okay, so here's how the graph is constructed. I construct a tripartite graph with two cubical complexes. The first cubical complex is used to construct the graph between the left and the middle, and the second is used to construct the graph between the right and the middle. Okay, so on the left-hand side, I'm going to have all the cubes of the cubical complex, and in the middle, I'm going to have all the vertices. And I put an edge between a cube C and a vertex B if the vertex B is contained in the cube C. Okay, so at least this is what one would call an incidence graph between the vertices and the cubes. And it's fairly natural to use this as the amplifier. I guess for technical reasons, which I also won't get into during this talk, that is not quite the graph that we use. Instead, here's a graph that we use. So here, I took the cubical complexes and I shaded certain special parts. And actually, the shaded parts, you should think of them as being shaded according to the Hadamard code on the k-dimensional hypercube. And what I'm going to do is I'm going to take this tripartite graph that I drew for you here, but I'm only going to keep the special vertices, namely the vertices which are in the parts corresponding to this Hadamard code. Okay, now this is a complete and honest description of the amplifier that we use and how we construct it from the cubical complex. Okay, and now just to go back and tell you all a little bit about how this circles back to proving lossless expansion. So we said that there were two combinatorial parameters that we wanted to get a handle on, which was the small set root k face density and the small set edge density. And we said any improvement over Ramanujan graphs would give a lossless expander. The interesting thing is the cubical complexes actually do slightly worse than Ramanujan graphs on the first point, but they do way better. They do drastically better on the second point, that it more than makes up for having lost something in number one. And yeah, that's it for the technical portion of the talk. So now I'll just have a slide where I'll give some concluding thoughts and some open problems. So okay, the one of the main takeaways of this talk is there's a pseudo-random object that we were after, which is lossless expanders. And the way we approached this was by using some kind of product between an amplifier and a small version of the same pseudo-random object. And this is actually not a new idea. It's a fairly common paradigm, especially in like error correcting codes, and Simpson Spielman used this to construct efficiently decodable codes and such. And often in a lot of applications of this paradigm, one chooses this amplifier to be a spectral expander. And this has taken us quite far. But I guess more recently, a new trend, which has actually enabled progress on several long-standing problems. Most notably, I want to point out two problems that were solved 3 years ago. That is constructing good quantum error correcting codes and also constructing locally testable codes. So in these works, the main innovation in some sense over the age-old paradigm of amplifying a pseudo-random object was instead of using a standard spectral expander, you use some high-dimensional expander-like object. In some sense, these works on quantum codes and locally testable codes used a two-dimensional version of the cubical complex, which they call the left-right Cayley complex. And I just wanted to point out that there's still a lot of uh, open problems in this area of getting explicit constructions of pseudo-random objects. Like there's a problem in geometry which has to do with constructing subspaces where the L1 norm is a very good approximation of the L2 norm, the so-called Euclidean sections problem. Then there's a question of like getting a quantum version of locally testable codes or getting explicit RIP matrices, which can be used for compressed sensing. And in light of this new trend, these problems might be worth revisiting. And with that, I'll conclude my talk. Thank you all for coming.
Thank you very much, Sidhanth, for the nice talk. Are there any questions? There is one question in the chat. So,
Okay.
what goes wrong with using an abelian complex as is?
Right. So if you use an abelian complex, you would actually be able to construct logarithmic degree lossless expanders. The reason is if you have a Cayley graph on an abelian group, you actually need at least log degree in order to see expansion. And expansion of these subgraphs of this complex is a property that we crucially would need to use in our analysis.
Yeah. Okay. Someone is asking for some reference for cubical complex.
Yes. Okay. So there are a bunch of papers in the math literature, uh, such as one of Rungtana Peram, Sticks, and did shoot. I'm not able to recall the name. I think it was Vedernova. Um, but actually, in our paper, we wrote a section with like a computer science friendly introduction to these complexes. So I would recommend reading that.
If there are no further questions, then let's thank Sidhanth again.